Assalamualaikum and good evening everyone. Hi. Okay, so before we start, let's introduce ourselves first. So I start first. My name is AMIRA NURNISA binti AZMI. You can call me AMIRA. Evelyn, can proceed.
My name is NURSHAZLIN binti KHAHALANG. You can call me SHAZLI.
My name is LEONG. You may call me Lai.
My name is FARAH NAJIEHA, and you can call me FARAH.
My name is NURHANNA.
Hannah, you are muted.
Oh, I said just now, I think my internet is lagging. Do you hear me? No.
No,
Yes.
Yes, now can.
Okay.
Before cannot.
Are you lagging?
Okay. My name is NURHANNA bin Shardin. You guys can call me Hannah.
Hi everyone, my name is TASHMITA LOGESSPARAN. Metric number is 203213 and you can call me Tash.
So today we'll be discussing about the making of data sheet for Pfizer, Moderna mRNA nanoparticle vaccine. So as we know that this mRNA nanoparticle vaccine have been used around the world. However, they are lacking in the physical characteristic on the nanoparticles that have been used to make the vaccine. So today, as we discussed before, we will focus on 5 physical characteristic, which is first size, second PDI, third encapsulation efficiency, fourth electron microscopy, which is SEM and also DEM, and the last one is zeta potential. So maybe along the way we can like having suggestion or question when someone presenting their ideas. Okay. Who do the size? We can start.
Okay, let me share the first characterization, which is size. Sorry, my Zoom is lagging for a bit. Why?
It's okay.
I cannot share my screen because it's a bit lagging. Can someone please share?
Oh, Farah. So maybe someone else can start or can share your opinion about any characterization method.
I think maybe we can add the information for the FTIR. So basically, although the information for FTIR is not available for the lipid nanoparticles or solid lipid nanoparticles of the mRNA vaccines, but then because they already disclosed the ingredients, which is the type of vaccines used for the nanoparticles, so based on the chemical structures of lipids, we can deduce what kind of effect should be expected on the FTIR spectrum. So basically, for example, the lipids normally have the ester bonds and they have the hydrocarbon chain. So we can expect to see some stage 2, some kind of stage 2 peaks, or the ester bond has another kind of peak. So these are the peaks that should be expected on this method as well.
Yes, I believe also from FTIR we can like differentiate between which lipid nanoparticle having the mRNA and also which one doesn't by seeing the what component that align and not. Anyone? But I still believe like when I search the information about FIR regarding the Pfizer or Moderna, it doesn't like showing the result about it. It doesn't make the FIR result based on the FTR. Okay, Farah have
Yes, true. I think
Yes, Hannah? Yes, Hannah.
there is
Continue.
limited study.
Mhm.
Okay.
Yes.
Am I again? No. Oh yeah.
Hannah, you can press.
I think okay. I think the study is still limited.
Yes, I agree.
While waiting for Farah, maybe you can proceed with the next one. This.
So anyone what I would like to share your forecast of information? Lai, do you want to share first?
My laptop hasn't joined the Zoom. If you want to share, so we'll have to wait a minute because I'm using 2 devices.
So is it
Other than FTIR, we have TEM, right?
yes, the
Yeah, we also have
Transmission electron microscopy. Yeah, so it characterize solid nanoparticle, solid lipid nanoparticle. So do I need to share the document?
yes, if you have any figures you want to share.
Okay, wait, I will share. Okay, so I put my point in our document. So we actually can study the particle size or size distribution of mRNA for solid lipid nanoparticles using TEM. We know that TEM produce image based on scattering electrons transmitted from sample. TEM produce 2D projection image while SEM produce 3D projection image. So based on my research from internet, so this is the figure that I found. This figure shows that the transmission electron microscopy image of RNA encapsulating LNP. Okay, I'll start sharing. So do you guys have any opinion to characterize the nanomaterials?
Yeah, I need someone's help to share screen. I'm unable to do so. To show my figures. So can someone help me?
Yeah, I can share.
Thank you.
I'll share again. All right. Which one is your figure?
Mine is on top. PDI is on top.
This one.
Okay.
This one.
Yeah. But I need to see. Okay. Yeah. Figure 1 and 2. Okay. So shall I start now? Okay. So basically Okay, this is my prediction actually. Based on my knowledge of technology, I predicted so something like this will be observed. So as you can see in figure 1, because when we run DLS, it gives us two information, right? One is about size and PDI. So I just want to relate both of them, size and also PDI. So in figure 1, before the addition of mRNA, there's only solid lipid nanoparticles, right? So the size is much more smaller. But then when we add mRNA, the size will be larger. So therefore, the PDI should be lower. Okay, before the addition of mRNA, the PDI should be lower because it's uniform, smaller, and monodispersed. Monodispersed because it's like all of them are similar in size. But then, as you can see in figure 2, I think I've indicated a sharp peak. Okay, I think it's in orange color. That indicates the PDI is low. So when you see a sharp peak, it's okay. That shows that it's only SLN and there's no mRNA and the PDI is going to be low. So when mRNA is added, there will be a mixture of nanoparticle, which means like when you put a small amount of mRNA, the samples, one group of samples, they would have mRNA. Another one, they will have empty nanoparticles without mRNA because we didn't put enough mRNA. So there will be like high PDI. High PDI means variety of sizes, larger one, smaller one together. Larger because we have solid lipid nanoparticles along with mRNA. It is smaller because we have only solid lipid nanoparticle without mRNA. So as you can see in figure 2, you can see a broader peak for solid lipid nanoparticle along with mRNA. So that indicates that the PDI is basically high. And the PDI can also match our before values. That means when we put equal amount of mRNA, that means all the nanoparticles, every single solid lipid nanoparticle is going to receive all the mRNA, then they would have the same size. That means we will end up getting the more dispersed nanoparticles, but then it will be larger compared to the before one, because now they contain mRNA, right? So they would be larger, but then all will be same size because all of them receive the mRNA. So that there will be no change in PDI when you compare to before. So this is from what I studied. So yeah, thank you so much.
Yeah, I would like to add on. I believe the PDI would also predict whether there is any aggregations between the nanoparticles, because if there's any aggregations, then the PDI may increase. Yeah, so in the case that you mentioned just now, so it's basically in the perfect scenario whereby there is no aggregations occur. So this is an ideal scenario for our vaccines.
Yes, and also I would like to add a little bit about the DEM, right? So DEM, we like what we can differentiate between DM and SEM is like DM we can like look further into our what particles or our samples. Like SEM we can just look on the surface, but in DM we can look inside our particle. So I think from here we can see our mRNA inside our nanoparticle, right? Anyone have any?
Yes, I agree with AMIRA. So I would like to share mine. SEM. Wait, Okay. Can you guys see?
Yes.
Can you guys see the picture?
Yes.
Okay.
Yes,
Basically, SEM is used to observe the morphology surface of the samples, like Amira said, and SEM produced 3D image. So we can see here from the image, SEM provide higher resolution, which we can see that the mRNA solid nanoparticle was spherical in shape. So this is from my prediction only. Also, we can see from the 50,000 magnification, there is an agglomeration, agglomerate nanoparticles. This agglomeration occur due to the gold coating. And according to Omwoyo, the particles must be coated with gold to minimize the effect of heat during high power magnification. So that's why there is an agglomeration. And we can see the difference between TEM and TEM produced 2D, while SEM produced 3D image. So anyone would like to share yours? That's mine.
I can share mine. I joined the another time somewhere. We're able to see the slides.
Yes, you can see your slide.
So basically, I will talk about the encapsulation efficiencies, which is very important because currently we are encapsulating our mRNA vaccines using the solid lipid nanoparticles. So the higher the efficiency, the better it is. And basically, encapsulation efficiencies measures how well our mRNAs is encapsulated with the lipids. So basically, we can get this value indirectly by measuring the concentrations of the total mRNA as well as the free mRNA. So from this value, we basically calculate the encapsulation efficiencies by using the formula in the middle, which is total mRNA minus free mRNA, and then divided by the total again. And then we multiply this value with 100%. This is how we got the efficiency value. So to measure the total mRNA concentrations, the solid lipid nanoparticles will be disrupted in the organic solvent to release the mRNA. And then the mRNA will be measured by UV visible spectroscopies as the total mRNA concentration. And then from these concentrations, we will derive the amount of total mRNA from its amount, which is in milliliters. And we also determine the free mRNA concentrations and the samples containing the solid lipid nanoparticles, and that is loaded with the mRNA will be centrifuged to separate the mRNA loaded SLN from the free mRNA. And this solid lipid nanoparticle will be precipitated as the tablets, and then we will take the supernatants because it contains the free mRNA, and then its free mRNA's concentration will be measured for its amount, and then using the UV visible spectrometry as well. Yeah, this is how we got the values for the total mRNA as well as free mRNA concentrations. And of course, the higher the efficiency or the higher the encapsulation efficiency, the higher the amount of mRNA encapsulated. So therefore, it's a good encapsulations if the value is as close as 100% as possible. If the value is 100%, it means all the mRNA are encapsulated. So we want it to be as close to 100% as possible because we want almost all mRNA to be encapsulated. Yeah, and this value is influenced by the amount of mRNA. And this is a prediction. So as the amount of the mRNA increases, so the efficiency would increase initially. But then after a certain point, because the depletions of the lipids would cause some mRNA fail to be loaded, and hence the efficiency will drop when there is a further increase in the mRNA content. Yeah. So basically, this is the end of my sharing. You may share your thought or share your slide as well, or either is a document as well.
Before we going further for our discussion, maybe we need to stop first because our Zoom the time is up, and we enter the new link after this. Okay, see you later. Okay, hello again everyone. So we'll proceed our discussion. So before, Lai has shared about encapsulation efficiency. So I would like to add a little bit about, like, as we look for Pfizer vaccine, they have used a few types of lipids that helps to encapsulate the mRNA better. So, for example, is the ALC0315, which it helps to regulate the release of mRNA in the lipid nanoparticle. So, and then the second lipid that we use is PEG, lactate lipid. It helps to form a protective hydrophilic layer, and this helps to stabilize the lipid nanoparticles to encapsulate the mRNA. So it reduces the non-specific binding. So actually there are a lot of components that have been used by Pfizer to make their vaccine becoming better. Anyone want to share any information that you know about that?
I just want to add regarding Tashmita's point earlier, which is regarding the size. Let me share my screen. So in my graph that I draw, actually by using the LS, we can measure the Brownian motion of macromolecules, which cause the random changes in the intensity of light scattered from a suspension or solution. In measuring the size of nanoparticle vaccines, I think the characterization of size is important because we want to know whether the mRNA vaccine is successfully encapsulated in the solid lipid nanoparticle or not. So by using the LS, I think we can know whether the mRNA is in the SLN or not by looking at the increase in size, which we can see in the graph that blank SLN has smaller size rather than the mRNA encapsulated with SLN, which is I predicted around the highest intensity peak here is around 200 nanometer. I think that's all that we can get from the LS.
Anyone want to add about what Farah said? Okay, thank you, Farah. Also, I would like to share my opinion about one of the characterization that we can done for our mRNA lipid nanoparticle vaccine, which is zeta potential. So basically, zeta potential is characterization using surface charge of the nanoparticle. So I would like to share some graph. Okay, so before I proceed, the zeta potential can be influenced by the pH, which pH is the distribution of H plus ion, and also Pi. Pi is isoelectric point, which the pH is at the pH at the surface charge of the nanoparticle is 0. Okay, so basically most of the vaccine producer they're using zeta sizer nano ZSP to measure the zeta potential. So first things that zeta potential can be used to characterize stability of mRNA LNP vaccine, which here you can see that there are 5 of lipids that have have been commercialized to be used to encapsulate mRNA, which is the ODMA, KC2, and more. So if you want to make a vaccine, maybe we use the ODAP Zeta. The PI is 5.39, right? As you can see here, the black one. Okay, but we cannot use PI, the pH at the PI to make our medium for conducting or measuring zeta potential, because during that time our nanoparticle doesn't have any charge, so we cannot run any measurement for zeta potential. Okay, so from here, what I want to say is, if we want to make a vaccine, mRNA LNP vaccine that are stabilized using zeta potential is from here, zeta potential vaccine that use zeta potential more than positive millivolt, positive 10 millivolt is we can use that if you want to make highly positive vaccine that are stable. But if you want to make a vaccine that is stable but highly negative positivity, we need to refer or choose that the pH when the zeta potential is more than negative 10 millivolt, something like that. So from here we can what I would like to conclude is zeta potential can be used to make a stable vaccine from based on the surface charge. And next, the zeta potential also can be used to characterize the formation of mRNA lipid nanoparticle vaccine. For example, here you can see that the black one is only the lipid nanoparticle, right? And then the red one is the mRNA, the lipid nanoparticle that have the mRNA. So by using zeta potential, we can differentiate which lipid nanoparticle that have the mRNA and which are not have. Why we can do this? Because the lipid nanoparticle is negative charge. I'm sorry, positive charge. The mRNA is negative charge. So the zeta potential, when lipid negative, lipid positively charged, mRNA negatively charged. So when we produce our vaccine, it will become highly positive. However, the positivity is a little bit reduced. So that's why we can see that when we add mRNA in our lipid nanoparticles, the red one, the zeta potential a little bit decreased because the mRNA have reduced the positivity charge of the lipid nanoparticles. So from here, we can differentiate whether it have mRNA or not, and then we can see how the presence of mRNA can make a changes to our zeta potential. Okay, the next one, zeta potential also can be used to characterize durability of mRNA lipid nanoparticle vaccine, which we can see that from here, when our vaccine is freshly prepared and then it being froze in the refrigerator for 4 weeks, and then after that maybe in room temperature for 1 hour, 2 hours, 48 hours, we can see a decreases in zeta potential. This is because the mRNA have been degenerated, or the mRNA have leakage or going out from the lipid nanoparticle. So that's why zeta potential increases, because mRNA is reduced, so the positivity charge of the lipid nanoparticle increases. So from here, I would like to conclude that zeta potential can characterize our mRNA lipid nanoparticle vaccine by stability, and also formation. Okay, that's all from me. Okay, anyone want to share anything?
I do agree with you that the measurements of the setup potential is very important, because as we know, when the setup potential is either very large or very low, which is smaller than -10 or larger than 10, +10. So it basically means that they are actually charged enough and then they will repel each others. So there is relatively a lower risk of agglomerations, which is what we want to avoid in our vaccine preparations. Yeah, I'm not sure whether others have the same opinion as mine.
Yes, truly. Anyone want to add anything?
I want to add on PDI. Since PDI can use to determine stability of our nanoparticle. So how to know our nanoparticle are stable or not? We can see from PDI value, right? So the value for stable nanoparticle is between 0 to 0.1, and for if our PDI value is above 0.6, so our nanoparticle is not unstable. It's not stable. Okay. Anyone else wanna add your opinion?
Okay, no one? Okay, if that, okay, if that's all, I think we have going through 6, right? 6 characterization, which is size PDI, and then FEIR, what else? Zeta potential, and then encapsulation efficiency, and also we have touched about electron microscopy, CEM, and also DM. So I believe all the result or the forecast prediction that we have done can contribute to our data sheet for our mRNA lipid nanoparticle vaccine. Okay, I think that's all from us, right? Okay, thank you everyone.
Thank you,
Thank
Mike.
you.
Thank you.